Okay, we are live. Audio and video is up. Welcome back to Structures. I haven't yet graded your exam, but my goal is to get that graded by Friday. I have another exam in another class next week, so I definitely want to get it graded before then. Usually I try and knock it out really quickly, but we were talking right before class. I just a lot of stuff came up, advising and whatnot. Just didn't have time. I do want to mention, though, a couple of things outside of structural analysis before we begin our topic today. First off, I want to talk about steel design. So as you're aware, we're offering structural steel design next semester, and if you go onto the schedule lists that there is no textbook for steel design. And that's true. There is no textbook. I don't use a book, and here's why I don't use a book. In order to do steel design, you need the steel manual. And you know, when we were back on campus, you probably saw students with steel manuals. Here, I'll even turn my camera off so that you can kind of see it. Or share. So this is the steel manual here. You pretty much have to have this to do steel design. You can't do steel design without it. And the way that it works, the way that the discount program works, so if you were to go onto AISC's website right now and just try and buy it, it's something like $360 or $400. It's a pretty expensive book. But for students, AISC has a discount program which drops the price substantially. It goes from, I think it's like 135 or 140, something like that. So it's a market decrease. You pretty much have to have the manual. So as a result, I don't make you buy a textbook. So here's what will happen. For those of you that are interested in taking steel design next semester, I advise you to register for the class sooner rather than later. I've requested my coupon code through AISC. Once I get that, I'll distribute that to all the students that are registered, and then if you can, what'll happen is you'll go onto AISC's website, purchase it yourself, and then AISC will ship it right to your house. We won't need the manual like on day one, but maybe like by the second week and definitely into the third week, we're going to be using it every day. So make sure that you get a copy. If you want to borrow one from a friend, like I'm not going to say no to that. But I do think this is a really valuable resource. Like if you go to just about any practicing civil engineer and look at their bookshelf, this is like a staple in the library of a civil engineer. And so I think it's a really valuable purchase. There's a lot of really good info in there, and so I do want to mention that. But I just wanted to make sure that everybody was clear, so that if you register for the class and there's no textbook, and then you get an email from me saying you need to buy the manual, you're like, what the heck? I wanted that to be clear. The second thing I wanted to mention before we get started, I don't have this on the slide, but I wanted to mention this. So we received an email from Toyota Manufacturing, the Toyota manufacturing facility that's in our region, and they're actually looking to hire some environmental engineers, and they're looking to hire them very quickly for co-ops and internships. If you're interested in that, just send me a message, like either in the chat or after class, because they're really looking to get some folks on soon, and that's money, that's a job and experience during these times. That's a really valuable opportunity. So if you're interested in that, let me know, and let me know quick. Like I said, they're trying to hire. Okay, I see one. I already see one chat. I will get in touch with you. Okay, for the folks that are messaging me, here's what you need to do, and do it like sooner, like almost like now. Get your resume prepared, like now. If you don't already have one ready, then that's good. But if you don't already have one ready, get it ready. If you do have one ready, go ahead and send it to me. Go ahead and send me the your resume as a PDF, and then I'll get it moved through the pipe. But I just want to throw that out there. But if you're interested, get me your resume like now. Okay. Let's talk about our topic today. So some of you might look at the username. You might see I put red pill or blue pill because we're talking about matrix analysis. So I had to throw a little pun in there. Today, what we're going to do is we're going to begin the discussion of something that really it's like the beast that we really want to slay as structural engineers, and that's handling indeterminate structures. Up until now, everything that we've done has been for a determinate structure. So let's back to what is, like, how do we classify structures? This was like something we did at the very beginning of the semester. We started to classify structures, and we classified them as unstable, stable and statically determinate, or stable and statically indeterminate. Okay, so what's the difference between a determinate structure and an indeterminate structure? If you remember, indeterminate structures have more unknowns. They have too many unknowns than just equations of equilibrium, right? If you have like for example, if you have a beam and then you have a hinge and a roller, okay, that structure is statically determinate because there's 1, 2, 3 three reactions, and we have 1, 2, 3 equations of equilibrium. So this structure is statically determinate. Okay, there's 3 unknowns, 3 equations of equilibrium, so I can get an answer. Okay, but what you'll find a lot of times in real life is you don't have just this going on. You have maybe a roller here or a roller here, and so what comes with that roller is another reaction. So not only do we have 3 equations of equilibrium, but now we have 5 unknowns for just the example I've drawn here on the slide. So this structure would be a structure that's indeterminate. Okay, and so for this structure, we don't have enough information with just this. That's not enough. We have to develop new pieces of information in order to solve the structure. And the short answer is, in order to solve an indeterminate structure, you need to have an understanding of the relationship between forces and deflections. And so that's why we hold off on looking at indeterminate structures until later on. You really need to have a solid understanding of your shear and moment diagrams, your truss analyses, deflections and trusses, deflections and beams. You got to understand that stuff before you can start to grasp how an indeterminate analysis works out. Now, one of the things you'll find is that, and I'm not going to sugarcoat it, indeterminate analysis is just more involved. It's just more complicated. There's more going on. And so I'm always one that's trying to ground it in reality. And I ask, if it's harder, then why the heck would you do it? Like, why make it harder on yourself when designing? Why use an indeterminate beam if I could just use a determinate one? There's some very clear reasons why you would do that. And so I want to talk about that first. Why use indeterminate structures? Why make it more difficult? Well, there's 2 like really obvious reasons as to why you would use an indeterminate structure. The first is your end results. Your end results will contain less forces and smaller deflections. If you have a structure that's indeterminate, because you've got extra reactions, you've got extra supports, the structure itself is seeing less internal forces and seeing less deflections, and so that saves you on money. Okay, so for instance, I know this is a little hard to see on the slide, but I'll sort of say it verbally. Okay, let's take a look at this beam, and let's take a look at this beam. Okay, now the difference between these 2 beams is the one on the left is a simply supported beam. We have a pinned boundary condition on one end and a roller on the other, and the one on the right has fixed boundary conditions. Okay, now because the one on the right has fixed boundary conditions, it's indeterminate. This is a statically indeterminate structure. Okay, and as a statically indeterminate structure, there's more unknowns than there are equations of equilibrium. But what I want to show you is what happens when you're done with that analysis. Like, once you go through and you complete the analysis, what do you get as an end result? The first thing that's worth looking at are the deflections. Okay, if you look at so this is the same beam, the same geometry, the same length, the same load. Everything's the same except for the boundary conditions. One's determinate and one's indeterminate. And when you look at the indeterminate beam, the indeterminate beam's deflection is 20% of the determinate beam's deflection. The determinate beam has a deflection of 5 WL to the 4th over 384 EI. The fixed beam has just WL to the 4th. So the one on the right has 5 times the the one on the left has 5 times the deflection the one on the right. So that serves the structural engineer a benefit. They can use a smaller beam because they don't have to account for as much deflection. That saves them money. Also, the same thing on the moments. Like, when you look at the moment diagram, you can see this is like WL squared over 8. This moment here is like WL squared over 12. This is WL squared over 4. There's less bending, less deflection, and so it saves the engineer and ultimately the client money. If this is a bridge, the client is the state. If it's, you know, a building, the client is whoever's, you know, constructing the facility. So there's a real impact on why you would do that. The other impact is on the concept of redundancy. So the topic of redundancy, what I mean by redundancy is if you have an element in if you have a structural system and an element fails, can the system maintain its stability after that element has failed? So for instance, if you look at this beam and this beam, those two beams are exactly the same, but the difference is this one right here has an internal hinge. This one does not. And so the one on the right is indeterminate, and the one on the right is determinate. By putting that hinge there, you make the structure determinate. So yeah, it makes the analysis easy. But what happens if the pier fails? Like, what if this is a pier in a river and a barge comes and knocks the pier out? Well, if you have a hinge there in the beam, yeah, it makes the analysis a little easier. But with that pier gone, now the structure is unstable. Okay, at least if the pier is gone, the structure is statically stable, so it has a chance of redistributing and carrying that load after that element has failed. So there's some very real reasons why you would do this. So it's not Dr. Mike just making it complicated just for the sake of making it complicated. There are reasons why you would do it. Okay, but now let's see. Okay, that's fine. Now let's talk about how we would handle this as a structural analyst. Okay, so I have here a problem, and I just made this problem up. There's nothing special about this problem, but it's something to sink your teeth into. Okay, so I have a beam here, and it's an indeterminate structure. It's indeterminate to the first degree, okay, and it's 40 foot long, but it has a support right in the middle. So two spans that are 20 foot long apiece. It's made of steel. So the E value is 29,000 KSI. It has a moment of inertia of 1,200 inches to the fourth. And I came up with a loading scenario that was purposefully not symmetric, because I make it a point that not all structures and structural analysis problems are symmetric. So we have a load, and then we have a distributed load, and then we've got this 20 kip load off to the side. So we can't even exploit symmetry. Okay. And so I want to make sure that we're clear. There's one too many unknowns. We have 4 reactions, right? Now I know I can determine one of those reactions. Just I can say the sum of the forces in the x direction equals 0. So I know that the horizontal reaction at A is 0. Like, that's fine. But there's 4 reactions, and I only have 3 equations of equilibrium. So there's one more equation we need to solve this problem. Okay. Now, in order to solve it, what we're going to do is we're going to use the relationship between forces and deflections. Okay, and so what I mean by that is I'm going to ask this very simply, very basic. What is the deflection at B? Make sure everybody's paying attention. Like, what's the vertical deflection of the beam at point B? I promise it's not a trick question. It's 0. Exactly right. So let's talk about your 4 equations. What are the 4 equations? We have the sum of the forces in the x direction equals 0, the sum of the forces in the y direction equals 0, the sum of moments about any arbitrary point equals 0, and the 4th equation is that the deflection at B equals 0. Okay, and so that's one way of assessing the problem. Okay, so one way you could do this problem is you could say, okay, let's choose the support at B. Okay, and so you'll see where I'm going with this here in a second. So I think hopefully we agree that the deflection at B equals 0. So imagine if I take this beam and I kick out the support from B. I remove that support from B and I allow that beam to deflect. Okay, now if you take out that support at B, I have a simply supported beam with a distributed load and a point load. We just had an exam on computing deflections in beams. I know that you could tell me what the deflection is at point B. I've given you all the data. So you go through and chug it out. And for this problem, once you chug it out, you get a deflection value of like 4.22 inches deflecting downward. If I remove the roller at B, then the beam deflects downward 4.22 inches. Okay, but in real life, we know that the deflection is 0. So if I remove that roller at B and it deflects 4.22 inches downward, the question then becomes, okay, what is that magical force required that pushes it upwards 4.22 inches, so that the net displacement, the net deflection is 0. And so if you compute that for this beam, like how much load is required to push that beam up 4.22 inches at support B, go through and check it out, you'll get a force of 63.75 kips. 63.75 kips, that's the reaction. That's the reaction at B, okay? The reaction at B is the force required to push that beam back up 4.22 inches in order to achieve equilibrium. Okay, and so now that you've got that one unknown, you still have the reaction at A and the reaction at C. Well, now you can just use sum of forces in the X direction, sum of forces in the Y direction, sum of moments to solve for all the others, and you get, you know, a reaction at A, a reaction at C. You can draw a shear diagram, draw a diagram. But that is a very basic way of assessing an indeterminate structure. This is like if we were teaching a class solely on indeterminate analysis, this would be the first method that we cover. We call it the method of consistent deformations because it pretty much is in the name. The structure's deflected shape has to be consistent. So the deflection at B has to have net 0 deflection. So we allow it to deform downwards, figure out how much deflection at B there would be if we allow it to deform, and then what's the force that's required to push it back up. That's the method of consistent deformations. Okay, does this make sense? Does anybody have any questions about this concept? Right now, I'm just talking about concepts. We're not talking about the math. We're not talking about the process. I just want to make sure the ideas make sense. Everybody good? Okay, now, here's the thing, okay? This is a method that I think is really easy to understand, okay? The problem with this method is that it's very difficult to program, okay? It's very difficult to write a computer program to do this problem, okay? Now, why am I talking about computer programs? Like, what does that matter? Okay, let's just live in the real world, okay? Let's say you're working for me, okay? I'm the principal at a structural engineering firm. You all are working for me as junior level structural engineers, and I say, okay, we're designing a new commercial office building. I need you to analyze this beam. I want somebody in chat to tell me, if I give you the problem and I say, I need you to analyze it, how do you think you're going to do it in real life? Like, let's be honest. How are you going to do this in real life? There you go. You're going to put it in RISA. That's exactly right. Or STAD or some other program, but you're exactly right. That's how you're going to do this in real life. If you open up your textbook, there are oodles and oodles of different methods in order to solve an indeterminate structure. What I'm going to show you is, in my opinion, the only method that matters, which is how RISA works. How does STAD work? How does RISA work? How does SAP work? How does all the programs that do structural analysis, what is it doing in the inside? When you click that little equals button on structural on RISA, it does something. I want you to understand what it does. Okay, but let's go to the specifics as to why it doesn't do this. What's on this slide? Why doesn't it remove a support from B, or remove the support from B, allow it to deflect, push it back up? There's a reason why. The problem is that in order for this method to work, I have to choose a redundant, right? So I go to that beam and I say, okay, I'm going to choose the support at B, and I'm going to allow it to deform. And it deformed 4.22 inches, and I pushed it back up. Well, why not the support at C? Why not the support at A? Like, as using human intuition, I think it was easy to look at this problem and to say, okay, if I look at this problem, I'm probably going to remove the support at B. That's going to make the integration easier. That's going to make the problem a little easier to do. And you're right, as a human being, removing the support at B seems to be the way to go. It seems to be what makes the most sense. The computer doesn't know that. A computer is just going to try and apply a process. And here's the other thing. This structure that we just looked at only had one redundant. What if we had a problem that had 6 redundants or 24 redundants? I mean, you could look at frames and buildings that could have hundreds of redundants. And so, think, okay, let's say a beam had, 3 redundants, so it has 6 reactions. I could poll this class, and Wheaton could say, well, I'll choose redundants 1, 2, and 4. And then Courtney might say, well, I'll choose redundants 1, 3, and 6. And so there's all these different ways of doing it. And each of those different processes results in a different, set of calculations, a different method across the board. And so it becomes incredibly difficult to program. Here's sort of the point. What we looked at just now was a method, the method of consistent deformations. We have sort of two classes of methods that we use for indeterminate analysis. One are what we call flexibility methods, and flexibility methods is where your goal is to solve for an unknown force, like an unknown reaction. But then we have stiffness methods, and stiffness methods look at it on the flip side and allow us to solve for unknown deflections. Okay, and so stiffness methods tend to be the way to go, and this will become clear as we progress through this week and next week, because as you develop the process, you find there isn't multiple different approaches. There's not multiple different ways of doing it. The benefit of a stiffness approach is that there's really only one way to solve the problem, and you get one answer at the end. And we'll talk about the theory as to why that works as we progress. But what I want to talk about today is give you a high-level view of how a computer does this, and then we're going to get into some math that we need to do with matrix algebra. So let me give you kind of a basis for how RISA and how any other computer program does structural analysis. And I want to start with a very, very, very simple problem. Okay, so let's look at a very basic problem, an axially loaded bar. Okay, so we've already looked at this problem in here, but this is a problem that you've done in mechanics of deformable bodies. It's a problem you've done in here. This is a really easy problem to understand. Okay, so I have a bar. It has some length L. It's made out of some material with a Young's modulus E. It has a cross-sectional area A. I take that bar and I yank on it with some force F. It responds by deforming some amount delta. Okay. And so we know from mechanics that the delta is FL over EA, okay? And so what I'm going to do is I'll take this equation and I'll rearrange it a bit. And what I'm going to do is I'm going to multiply both sides by EA over L, EA over L. So on the left or on the right side, it cancels and I'm just left with F. And on the left side, I'm left with this. So I'm just rearranging the equation, okay? And I'm writing it in this fashion because I want you to see the form that it's taking. We have that the force in the bar equals whatever the displacement is times this K. And I'm calling K EA over L, and I'm calling that the stiffness. Now, you probably have done problems like this before, right? You have some wall here. You have a spring that has some spring constant K. You take that spring and you yank it with some force F. And so if you yank it with some force F, F equals Kx. I believe you all have done those types of problems in physics, right? That should be something that you're familiar with. Everybody's seen this before, am I right? Okay, all right. So here's the thing. So what we have here is the solution for a single bar. And the point I really want to make is that analytically, this problem is completely solved. I know everything there is to know about it. If I know the characteristics of the bar, the E, the A, and the L, we can do this however you want. If you tell me the force, I can tell you the resulting displacement. If you tell me the displacement, I can tell you the force that causes that displacement. It's completely solved analytically. It's just plugging and chugging into this box. But the point I'm making is that we know everything there is to know about this bar. Okay? Here's the way I want you to sort of think about things. Okay? This is a bar. Now let's look at a truss. Okay, now let's look at a real world structure. Here's the thing. Isn't this just a bunch of bars? Like if we know the solution for a single bar, then a truss is nothing more than a collection of bars. Or really the term that I want to use is this term assemblage of bars. And there's a reason I'm using that term assemblage, because on Friday, we're going to talk about assembly, how you assemble a structure. And so the way that a computer sees a structure, the way when you go into RISA and you build your beam and you put your hinges and you put your boundary conditions and you put your loads on it, ultimately what RISA is going to do is it's going to take it and it's going to collapse it into this. Instead of, K delta equals F, it's going to be a K matrix times a displacement vector equals a force vector. Okay. And so it's basically going to convert it into a table of numbers. And the reason it's doing that is that's something computers love to do. They love handling, problems like this. Now, we've already done matrix algebra in here before, but the problem is, when we did matrix algebra, the only time that we've done it in here, we were looking at method of joins. We were solving 2x2s and 3x3s and, stuff like that. We were really getting into really big systems, but in real life, systems can get very big very quickly. This truss just on its own, after you apply the boundary conditions, is a 5x5 system. And in real life, you can have some systems that are really big. Like for instance, this image here on the right, I don't know, but that's probably, a couple thousand by a couple thousand. This one down here below could be even more than that. This one over here on the left is a finite element model that we developed in my research program. This is part of the tub girders that I've been doing research on. And so this is some really complex, really out there finite element analysis, but it's all built on the same principles. The same concepts work across the board. I know it may look funky and it may look complicated, but the computer sees all these problems the same way. It's just a bunch of springs being added together. The idea is that if you can determine the solution over one of these little regions here, which we call one of these little regions an element, then if I know the solution about one of those regions, then I can just use enough of them and determine the solution across the board. So right off the bat, and I'll mention this on Friday, but I'm going to probably use some terms interchangeably throughout our discussion of matrix analysis. And for instance, the term member, I might use the term member and the term element interchangeably. I might use the term joint and the term node interchangeably. Even when you start building joints in RISA, it numbers them like N1, N2, N3. The term node comes from finite element analysis, and I'll explain later what finite element analysis actually means, what matrix analysis really means. We'll be clear on that. What I want to talk about today is the math. I want to talk about matrix algebra. You probably did some of this stuff when you were in high school. Maybe you've done it a little bit in like Engineering 111. Maybe you did it in some of your math classes. But honestly, for a lot of times, I've been teaching this a long time, and by the time I get students in this class, this is something they haven't done in a very long time and gotten a lot of it. And I'm like, you know what? Let's take a day and let's just talk about the matrix algebra, because I don't want this to be an issue. And to be clear, when it's all said and done, y'all are going to be doing this like in Excel or something like that anyway. So that's fine. I just want you to get the high-level concepts. So first off, we've done matrix algebra before in here, and the big one was when we did method of joints, right? Remember, we would have a joint, right, and there would be two members that were diagonals, and we'd have a load on it, and we'd end up having something that we would plug into the Casio, right? We would have a two equations, two unknowns type of system, and then the Casio would solve out that 2x2 system and report that as, here's what X is and here's what Y is. But what the Casio is doing is it's performing computations according to the rules of matrix algebra. Now, the Casio is fine for if you want to do a 2x2 or a 3x3, but very often in structural analysis, the systems get much bigger than that. And so that's where computers come into place. What I want to do is cover the ideas, cover the concepts, and cover how software like Excel and MATLAB do this. You don't have to use MATLAB. I just do it in there in case anybody's interested. Okay, let's talk about some terminology. Okay, so what is a matrix? Now, a matrix is really just a fancy term for a table of numbers, a tabular array of numbers. And if you take a course in linear algebra, you're gonna you get you really start to focus on all the different aspects of like what's a rectangular matrix, what are vector spaces and all this stuff. I'm focusing on the stuff that matters to structural engineers. And so in structural analysis, we really deal with two types of arrays. We deal with square arrays and we deal with columnar arrays. And so square arrays are matrices that have the same number of rows and columns, and so they're square. In fact, probably what I'm going to be doing throughout, for the rest of the semester is when I say the term matrix, I'm just talking about a square matrix. If we're talking about a column of terms, I usually will just call that a vector. So when I use the term matrix, I'm talking about a square array, and when I'm talking about a vector, I'm talking about a columnar array. These are really the only two that we really deal with. In fact, to differentiate that, a lot of times when I write, I'll use square brackets to denote the matrices, and I'll use curly brackets to denote the vectors. So if you see me doing that, that's kind of what I'm referring to is the size and the dimension. One special matrix that you do need to be aware of is the identity matrix. The identity matrix is one that has ones along the main diagonal, and so the diagonal is anything along this stair-step path down here. So ones along the main diagonal and zeros everywhere else. That's what the identity matrix looks like. So this would be what a 4x4 identity matrix looks like. The reason why we call it the identity matrix is because it doesn't change a matrix with respect to multiplication. Think of the identity matrix as like the multiplicative version of the number 1, right? If I take the number 25 and I multiply it by 1, I get 25. It does not change the original number. So we call 1 the multiplicative identity. This is the multiplicative identity matrix. So if you take a matrix and multiply it by the identity, it doesn't change it. The identity matrix is also really the only matrix other than an inverse where the order of multiplication doesn't matter. You can take a matrix times the identity or the identity times a matrix, and you'll still get that original matrix. It doesn't matter. And they're very important in relation to inverses, and we'll talk about that here in a bit. All right. Let's talk about matrix operations, okay? And so we need to review some matrix operations because this is going to be stuff that we are going to be doing pretty quickly over the next few days. And so I want to make sure that we know how to add and subtract matrices, that we know how to multiply them by numbers, that we know how to multiply matrices, that we know how to transpose matrices, we know how to invert matrices. The inversion is probably the only one where I'm going to say, okay, that one you really need to use a computer if the problems get really, really big. Like a transpose, you could do a transpose by hand. You could do a matrix multiplication by hand. An inverse, it usually takes a lot of time if your matrices get pretty big. And we're going to be using some software to do this, okay? And I'll show you how this works in Excel because it's really easy. Before we break out Excel, I want to talk about some terms and some definitions, okay? So some important terms and definitions, okay? The first term that I want to throw out to you, and you might have heard some of this stuff before, but it's probably been a long time. So the first one is the idea of matrix symmetry, okay? So one of the operations that I want to show you is called transpose of a matrix. When you have a matrix that equals its transpose, where it and its transpose are the same, then that matrix is symmetric, okay? And so remember those stiffness matrices that I showed you a while back. One of the things that we're going to see is that stiffness matrices are symmetric. And so it's sort of a check to make sure that what you have done in your math is correct. Like if you do all the math and you find that the stiffness matrix is symmetric, then you did something right. That's a check. The two middle terms are arguably the one problem that matrix algebra and linear algebra is trying to address. So if we're talking about calculus, the two fundamental problems in calculus are what is the slope of a function, or what is the slope of a tangent line of a function, and then what's the area under a curve. And so we develop differentiation, derivatives, and then integrals to solve those two problems. The fundamental problem in matrix algebra is how to take the inverse of a matrix. Like that's like the big challenge. And so we have two different definitions. If we're looking at a matrix, it's either singular, it has no inverse, or it's invertible, which means it does. And when a matrix has an inverse, it only has one inverse. So a matrix and its inverse are like soulmates. They're partners in the stars. There's that matrix and its inverse they're the only ones that match. And so when you have a matrix and its inverse, you can take those two and multiply them, and you'll get the identity. And so the idea is this works with numbers too. Like, what is the inverse of 3? The inverse of 3 is 1/3, because when you take 3 and you multiply it by 1/3, you get 1. You get the identity. So numbers have one and only one inverse, just like matrices have only one and only one inverse. Now, one property that I am convinced probably most of you have never seen, but will show up here, is the property of orthogonality. And an orthogonality, this is a very weird property, but this is when a transpose equals its inverse. And you're like, when the heck would that happen? It does happen for a particular set of matrices, and we call those rotation matrices or transformation matrices. So this shows up in trusses when we have to adjust our coordinate systems. We'll see some orthogonality. Now, I have this slide here at the end. I'm not going to reference it very much in the presentation, because I'm going to show you how this works in Excel. But here's some operations that we need to do, and then here's how you would do them in either Excel or MATLAB. If I'm a betting man, probably most of you probably aren't going to want to use MATLAB in here, and that's fine. I think that Excel works very well for the visual assembly that we're going to see on Friday. But if anybody's interested, these are some of the terminology on how you would do that. But what I'm going to do is spend the rest of the lecture talking about Excel. Okay, so what I'm going to do is I'm going to stop the share. And if you go on to Blackboard on the lecture notes, you will see an Excel file right under lecture 34, and if you open the Excel file, it's going to contain these 4 matrices. I just didn't want to have to type them out over and over during the lecture. And so what I want to do is I want to go through some of these operations to make sure that you understand how this works in Excel. It's actually really easy, but I think this is pretty important. So let me share the screen. Come on. Okay, so here's the Excel file. What I did is I zoomed in a little bit, and I made the text a bit bigger so that you can kind of see what I'm doing here. So I have these 4 matrices, and I want to kind of show you some of these operations. Now, first off, there's no magic for defining a matrix. Like, if you want to define a matrix like the ID matrix, start typing in some values, right? That's the identity matrix. I'm just typing numbers into this rectangular region. Nothing major there. So first off, defining a matrix. I think everybody in here should be able to just define a matrix. It's just typing some numbers into cells. What I want to do is I want to focus on the operations. Okay. So first off, I'm going to pull these notes here on this other screen, because that way I don't have to go back and forth. Let's first off look at matrix addition and subtraction. So in order to add or subtract a matrix, you have to do this in such a fashion where you're just adding, well, first, to add a matrix or subtract a matrix, you're just adding them cell by cell. So for instance, if you wanted to do A plus C, you just do A plus C. You just add it term by term. So, copy, paste. And so all it's doing is it's just taking each one of those corresponding terms and it's adding them one by one. So a natural question might be, well, what is A plus B, right? So what would A plus B equal? And the answer is nothing, right? You can't add A plus B because the matrices aren't the same size. So that's one of the first things just to keep in mind, is that if you're wanting to add and subtract matrices, they have to be the same size. Let's let's talk about scalar multiplication. Okay, so let's delete this. Okay, so let's pick a matrix. Let's say matrix D. So let's say I wanted to multiply matrix D by 6. Okay. Well, in order to multiply matrix matrix D by 6, I'm just multiplying each term by 6. And so what you can do is that times 6. Bam. Copy, paste. Pretty easy, you know, not too difficult. And if you're wondering how I'm doing the copy and paste so fast, I'm just using the keyboard Control C and Control V. They're so, you know, some of the best shortcuts ever invented. Okay, now what we're really here to do, though, is we're really here to focus on the matrix operations that are new, that you probably have never seen before. Okay, and so I really want to focus on 3 formulas. Immult, I want to focus on transpose, and I want to focus on M inverse. Okay, so these are how you would do matrix multiplication. Here's how you would do transposes, and here's how you do an inverse. Okay, so let me delete these because I want to do one of these with you. Okay, so let's look at matrix A. Okay, let's take the transpose of matrix A. Now I want everybody to watch me. I want to show you how I'm doing this. Okay, now first thing that I want you to do whenever you're doing matrix algebra, make sure you've got plenty of room. Don't try and cram your calculations into one region, and I'm going to show you why. Okay, so what I'm going to do is I'm going to put my cursor right here. I'm on cell I2. Okay, and notice how there's a lot of empty space to the right of this and a lot of empty space below this. What I'm going to do is I'm going to say equals transpose. Now watch this. I'm going to drag over here, close that up. Watch what happens when I press enter. When I press enter, it automatically fills the rest of the cells. Okay. One of the things that you will find is if you try and change one of the cells in here, it gets upset. It gets upset because Excel sees this as one single computation. Okay, this is an array computation, and you can tell that you've done it correctly because if you start highlighting the cell, Excel draws like a big box around it and says, okay, we're recognizing this as one big formula. Okay, now I want to show you what a transpose is. A transpose is a very simple calculation, but I want to show you how it works. Okay, so here's how a transpose works, because I actually want to do this with you. Okay, so how do you do a transpose? The way that you do a transpose is this. Okay, so first off, when you do a transpose, the diagonal remains the same. So this term, and this term are going to remain the same. So this will be like 1 minus 2 and 1. But that's not going to change. But the way that you do a transpose flips the terms about the main diagonal. So for instance, this term and this term are going to exchange. So this will become 1 and that will become 1 because they're the same. But this one and this one are going to exchange. So this one's going to become 2. This one's going to become minus 1. This one and this one are going to exchange. So this is going to become 3. This is going to become 3. So what is the transpose of a matrix? The main diagonal remains the same, and flip all the terms about the main diagonal. This is something you can do by hand, but Excel will do that for you. Now, just to make sure everybody's paying attention, can somebody tell me what's going on with the C matrix? If I take the transpose of the C matrix, what am I going to get? And I want some responses in chat on this one. I get the same matrix. That's exactly right. If you take the transpose of matrix C, you get C. So because C transpose is C, that means C is metric. symmetric matrix. Okay, and we will see a lot of symmetric matrices in this analysis, particularly stiffness matrices. Stiffness matrices are symmetric. Okay, I hear somebody's microphone on. Does anybody have any questions?
Sorry about that. No.
No, you're fine. No problem at all. All right. Now I want to show you something. I got a couple more operations I want to show you. Okay. So okay. So let's now do some matrix multiplication. Okay. So let's say we want to do A times C. Okay. So in order to do this, what we do is we do M mult, and we do A by C. Okay. Now, whenever you're doing matrix multiplication, the order matters unless you're multiplying inverses together. In other words, A times C is not necessarily the same thing as C times A, and I'll show you that here in a second. What you do is you close that, and if you press enter, it does the whole thing for you. Okay. And I think you probably remember that pattern of how to do matrix multiplication, right? You take the rows and the columns and you trace it down. So that's something to keep in mind. But another thing that I will point out about so let's do C times A. Let's just see what happens. C. So see, you don't get the same answer. Okay. Matrix multiplication is not commutative. Okay, so the order matters here. The other thing I will point out about matrix multiplication is that whenever you use this mmult command, you have to, it only works for 2 arrays at a time. So for instance, if you wanted to do something like D times A times D, what you'd have to do is you'd have to say, okay, I need to do mmult of the first 2, then I have to do mmult of that and B. Let's do this. Let's make it C so it's a little easier to follow. Hold on. Oh, I put a bracket there. Whoops. This would be DAC. If you wanted to do DAC, you have to say, okay, I need to do D and A first, and then I need to take the product of that and multiply it by C. You have to nest it. It only works on 2 arrays at a time. Okay. Now, the other thing I do have another couple commands I want to run through real quick. So, for instance, if you want to do, let's do C inverse. So if you want to do the inverse of C, right? So inverse of C, M inverse, press enter. What you will find with matrix inverses is that more often than not, they're not pretty. Like when you take the inverse of a matrix in real life, you get a lot of like funky decimals. Matrix A is a special one. Like that one comes out pretty, but I came up with a matrix that would be pretty. But if you take the inverse of a typical matrix, you get a lot of funky decimals and whatnot in real life. Hence why a lot of times with matrix inverses, we tend to do that with software. But there's more reasons than just the funky values. Matrix inverses, like that process can be fairly involved. Now, I'll show you one thing that you can do. You can check to see whether or not that is correct, and you could say, well, what happens if I multiply the inverse times itself? And notice what it does to the formula. See how it says J7 hashtag, because it's saying I recognize that all of that is one big array. When you press enter, look what you get. You get the identity matrix. Now, I know whenever you do this in Excel, yourself, and it's probably kind of difficult to see because I'm zoomed in like this. Sometimes you won't get like zeros. You'll get 2 times 10 to the negative 19 just because of the way that the computer rounds it out. But for the sake of discussion, that's 0. Okay, one other thing I want to show you. So check this out. Let's do D transpose. Okay, so that's D transpose. And if you multiply D by D transpose, you get the identity matrix. D is a very special matrix. D is orthogonal because if you take D and you multiply it by its transpose, you get the identity matrix. So I crafted D to be a very special matrix. It's transpose. It's orthogonal. It's orthogonal because its transpose is its inverse. It doesn't happen all the time. It happens in very specific cases we'll see next week. Okay, we're running out of time. Does anybody have any questions before we call it? You all have a homework assignment where you're going to be doing some of these matrix calcs just to make sure everybody's familiar with the terminology, the math. I want to make sure this is doable. Any questions? All right, well, you all have a homework assignment on this, and on Friday, we're going to do a matrix problem start to finish in class, and I think you'll find it's a pretty slick process. That's all I have, everybody. I will see you all on Friday. Everybody stay safe, stay healthy. We'll see you then.